Hello everyone, good morning or good afternoon, good evening or good night, depending on which part of the world you are now. I'm now presenting a work joint work with Yingkai Ouyang. The topic is quantum key distribution with continuous variable, and the goal of our work was to provide a security proof that was able to take into account the imperfection and non-idealities of practical heterodyne detection. So as this is a summary of the talk, I will start with a few motivation about why we are interested in a continuous variable QKD, CV-QKD, what is continuous and what is not in continuous variable QKD, what is the goal of this work I'm presenting now, what is our approach, our methodology, what are our results and open questions. So first of all, why continuous variables? The main reason for looking at continuous variable is because continuous variable QKD is because these protocols are based on homodyne and or heterodyne detection for decoding, and these are mature components that are normally used in telecommunication, optical telecommunication. So a mature technology, and also they are scalable. The problems that we have to face when we deal with continuous variable are mostly related to noise. We need a big effort to reduce electronic noise to the minimum possible value, because this will affect the key rate and the distance. And also the security analysis and the theoretical security analysis is non-trivial at all, mostly due to the fact that continuous variable protocols are defined into a Hilbert space which has infinite dimensions. So what is really continuous in a continuous variable QKD? So what is continuous is are the degrees of freedom that we are using to encode the information into a physical system. Now the physical system is the quantum electromagnetic field, and most of the protocols, the information is encoded by the sender Alice using coherent states, and using the amplitude of the coherent state. Now the amplitude of the coherent state lives in the phase space, which is continuous, which is described by continuous variable, position and momentum, or quadrature and phase. And the same, of course, is for decoding, because Bob needs to access these, the receiver Bob needs to access these continuous information, and he will use homodyne or heterodyne detection to measure the quadrature of the field. Examples of the protocols that use this setup are GG02 by Grossans and Granger, 2002, and the no-switching protocol of Weedbrook and others of 2004. Now notice that these variables, quadrature and phase of the electromagnetic field, they are continuous and unbounded. Okay, they are two real variables. The fact that there is this continuous symmetry in this protocol is very useful from a theoretical point of view. A few very important theoretical results are derived using the continuous feature of this variable, the continuous symmetries of this variable. In particular, the asymptotic optimality of Gaussian attacks, which is very helpful because it tells us that in order to prove the security, it's sufficient only to consider Gaussian attacks from the eavesdrop. Another important result is the Gaussian definite reduction, which allows us to move from the asymptotic limit to the finite-size regime. And again, it is based on the continuous symmetry of these protocols. However, the quantities that we really measure when we go into the lab, they are not continuous because they are discrete, they are digitized, and they are bounded because any measurement device has a finite range. So the goal of this work that I'm presenting now is to assess the security of practical protocols where continuous symmetries are broken. So they cannot be exact, they are only approximate. The example I'm starting from this particular protocol, which is the non-switching protocol by Weedbrook and others. So Alice prepared coherent states. The initial protocol from 2004, the modulation was Gaussian. So Alice was sampling the amplitude of the coherent state from a Gaussian distribution. The receiver bulb measured by heterodyne detection, and here I'm talking about ideal heterodyne detection. So it's an exact measurement of the quadrature. So the output of ideal heterodyne detection is a variable which is continuous and unbounded. For this particular protocol, we have a lot of important results. We have this on the theoretical side. We have collect security proven against collective attacks by Leverrier 2015 and lifted to coherent attacks in 2017. This was presented at Qcrypt a couple of years ago. A lot of experimental demonstration of this protocol. In particular, there was one published just a few days ago in Nature Communication, and was also presented last year in Qcrypt. However, when you look at practical implementation, there are things you need to think about on both sides of encoding, from the sender side and the receiver side. About the encoding part, the ideal protocol in principle requires Alice to sample from a continuous distribution, but this of course is not possible. What you actually do in the lab, you approximate the Gaussian distribution with a discrete one, and this could be a route also to prove the security, to use some kind of continuity argument to map, to move from the ideal Gaussian distribution to a discretized version of it. But probably a better approach is to redefine a new class of protocols which are similar, but instead of using a continuous modulation of coherent state amplitude, they're based on discrete modulation. And so there is a lot of literature on this topic about discrete modulation protocols in CV-QKD. A couple of important papers were published in 2019 by Gorai et al. And Leverrier, and by Lin and others, including Lutkenhaus. There was also this work were presented in related works were presented in a Qcrypt last year, and more recently, also last year, we had analytical estimation of the key rates. Again, done as a result of the group of Leverrier. What kind of discrete modulation we are looking at? On the left, we have a few examples. There is a QPSK, which is 4-state on the left here, but it shouldn't be limited to that. We can have more states in the modulation. For example, here you have 4x4, 16 states in the phase space. Those are, of course, the amplitude of the coherent states or more. So instead of a continuous modulation, we have a discrete one. But there is not only the encoding side, there is also the receiver side, and this is the contribution of this work. So also the decoding in a practical scenario in the lab cannot be continuous and unbounded. As I said, measurements are digitized, they have finite precision, and any measurement device has a finite range, so they are bounded, cannot be continuous and unbounded. So it's obvious that if the bin size is small enough, if the range is large enough, we are expecting these practical discretized and bounded measurement to converge to the ideal case. But what is the impact on the security of the deviation from the limiting case? So this is the question we are addressing now. I want to quantify the impact of this approximation in the security of the protocol. That's the only way to achieve composable security. There were previous works that considered the discretized measurement, and very elegant work, very important, and where the security was proven using entropic uncertainty relation in 2012 from Farrer and others, and a few other works on this line of research. The approach is very elegant, but unfortunately in continuous variable QKD using entropic uncertainty relation does not necessarily give a tight bound on the key rate. So what is our case study? I will show you an example in which Alice, the sender, encodes using QPSK, so quadrature phase shift keying, 4 states on a square, 4 coherent state amplitude as input, and Bob measured by non-ideal heterodyne detection with a certain range in phase space and a certain number d of bins per quadrature. The security framework is that of collective attacks. First, I will talk about asymptotic limit, and I will use the Devetak-Winter formula for the key rate and estimate this quantity, the key rate, using a semi-definite program. And then I will look at finite-size correction and include them in a new formulation of a refined semi-definite program. The strategy to prove the security, and in particular to compute the asymptotic key rate, is to use the covariance matrix of the state. This is still possible, although the encoding is discrete. We can still evaluate the rate using the covariance matrix. And we use the semi-definite programming to find an unknown state with a certain covariance matrix which matches the empirical data. And doing this, we follow the work of Gorai and other, PRX 2019. And then, of course, the empirical data are not obtaining using ideal heterodyne detection, but they are obtaining using non-ideal heterodyne detection, as I discussed before. What are the main challenges in developing this program? The main challenge is that the Hilbert space is infinite dimensional. So we need somehow to truncate the state to a finite subspace, at least as a first attempt to solve this problem. And we need then to estimate the error due to the truncation, and then we can use a continuity argument of the entropic function, which entered the key rate formula. So this is an example of the SDP that we want to solve, and this is for estimating Bob variance. So the objective function to minimize is this one, and here you can recognize the operator which expresses Bob quadrature variance b dagger b plus b dagger. Then there is another operator which is a projector that accounts for truncating the Hilbert space. And then there are the constraints. You see here, you see 3 constraints. The first one is the expectation value of the variance operator. Now this is the empirical variance, so it's not the variance of the quadrature. So this is not the quadrature variance. This is the variance of the quantity that Bob is actually measuring in the lab. So you can see is a discretized version of the variance. And on the right, there is the empirical variance. So this is a quantity that you want to measure in the lab, which is the value of the empirical variance computed by Bob from the experimental data. Then there is another constraint which accounts for the fact that heterodyne has a finite range. So there is a probability, a finite probability that your measurement will go outside of the range of your device, and so we need to account for this with another truncation error, and then of course the last line is for normalization of the unknown state. Similarly, we have to also to solve another problem, another semi-definite program for the covariance. And here in the objective function, you will recognize an operator for the covariance of Alice and Bob quadrature and the truncation operator. And here are the constraints, and also here you can see one of the lines. You will see the expectation value of the empirical covariance operator. So once again, this is not the covariance operator of the quadrature. is the covariance of operator of the quantities, the observable, which are actually measured by Bob, which is a discretized version. And on the right, there is the empirical value computed by Alice and Bob. If we solve this kind of, if you solve these problems, we can estimate the key rate, and we can compare the result of a numerical estimation with the exact analytical result, which is provided by Bari and others last year. So that's a blue line for ideal heterodyne. And then we can compare these with our numerical result for non-ideal heterodyne with different ranges. R equals 6 or 7 in unit of shot noise. And here you can see that already with R equals 7 and D equals 16, it means 16 beams per quadrature, we have a pretty good agreement between the ideal heterodyne case and the practical heterodyne measurement. But these quantities, this plot is obtained using a cutoff in the Hilbert space. This works very well, but it's not very clear how to justify it, how we can justify this cutoff. So it would be better to have a way to do the calculation without using a cutoff. As I said before, this is hard because the Hilbert space is infinite dimensional. But what really matters is not if the Hilbert space is infinite dimensional, but whether the operators that we are dealing with are bounded or unbounded. Now, if we deal with quadrature operators, they are all unbounded, as we know very well. But the practical measurement that Bob is doing is not described by the quadrature operators, but by a bounded and coarse-grained version of them. And as a matter of fact, if you write down these operators for the covariance matrix, they are all bounded. So once we consider non-ideal measurement, the operators are bounded, and as a result, we don't really need the cutoff in the Hilbert space. So we can just massage a little bit the semi-definite programs, and we will write new versions which are not depending on a cutoff anymore. And the results are still pretty good. Of course, what happens if that having accounted for the cutoff, having avoided the cutoff, we need in general a larger range in order to approach the ideal setting, the ideal limit. But we can still see that with a range of 7 standard deviation, 7 shot noise unit. 7 standard deviation of the shot noise, we can still have a good agreement with the analytical ideal result and ideal case. Finally, we can put new elements into the semi-definite program to account for statistical fluctuation in entropic function through the asymptotic equipartition property. And we can also add statistical fluctuation in parameter estimation for all the quantities, the variance and the covariance estimated by Alice and Bob. If you do this, we can move away from the asymptotic limit and compute the key rate for finite size. And here you have some example for 10 to the 10, 10 to the 11, or 10 to the 12 signals sent. As you can see here, we need a fairly large block size to approach the asymptotic limit, but at least this shows that it is possible with this method to have a non-zero rate even in the finite block length scenario. In conclusion, we can compare this work with the previous theoretical works, and what we have done new here is to consider discrete modulation, the security of the discrete modulation protocol in a composable fashion, but where the heterodyne detection is not the ideal model for it, but is a model which is more close to realistic implementation. Next step is to use a non-linear semi-definite program, like in the work of Lin and others from the Lutgenhaus group, with this kind of nonlinear optimization is expected to work much better. And then the other improvement is to improve the error analysis to reduce the block size. In fact, our estimation of the confidence interval for the finite size security analysis is far from being optimal, and there will be room for improvement. Thank you for your attention.